This first video will be for the summer work packet, specifically the Math Review Part 1. In this section we have to work with scientific notation, Scientific notation is used to express very large and very small numbers quickly without changing the number of significant figures. Correct scientific notation will always be a number between 0 and 10 times 10 raised to some power. So for example, 5.12 times 10 to the 9th meters is correct, whereas 51.2 times 10 to the 8th meters is incorrect. 51 is a number greater than 10, so that is incorrect. In order to convert between the two, if we're starting with standard notation and turning it into scientific. For instance, if we have a number 152900000 seconds, so that is 512,900,000 seconds, we're going to start by copying down our significant figures, 5, 1, 2, 9. We're then going to put a decimal so that this number is between 0 and 10, 5.129, times 10 raised to a power. To find that power, we're going to start with our standard notation number, find where the decimal is. How many times do we have to move it to put it where it belongs? 1, 2, 3, 4, 5, 6, 7, 8 times. Times 10 to the 8th. This is going to be a positive 8th because this is a big number. And then we also have to copy down our unit. On the other hand, if we have a number like 0.00120 meters, to write this number in scientific notation, we're going to do the same thing and copy down our significant digits. 1.20. If you're having trouble remembering significant figures, you need to check that out, find a YouTube tutorial or something along those lines, or come in for tutoring. Times 10 raised to a power. That power is how many times we have to move 1, 2, 3, our decimal. So it will be times 10 to the 3rd. However, this is a small number, so it will be negative 3rd meters. Going from scientific over to standard notation. If I have a number like 1.82 times 10 to the 3rd watts, we're going to do the same thing we did before. Copy down all of our significant digits. We have a 1, an 8, and a 2. Then we're going to take our decimal and move it 3 times. Because this is a positive 3, that means it's a big number. So we're going to be moving it to the right, because when we move the decimal to the right, it gives us a big number. 1, 2, 3. So that will give us 1,820 watts. We can do the same thing for small numbers. 6.24 times 10 to the negative 4th joules. I'm going to start off by writing down our significant digits, 6, 2, 4. And then we're going to move the decimal 4 times to the left this time because it's negative, and negative means a small number. 2, 1, 2, 3, 4. And fill in our zeros. 0.000624 joules. Using scientific notation in your calculator. There are 2 options. We're going to use the number 5 times 10 to the 3rd, and we're going to talk about the two different ways that we can represent this in your calculator. The first method is probably the easiest. You're just going to type 5 multiplied by 10 caret 3. The benefit of using this method of writing scientific notation in your calculator is that it's usually a bit easier to enter. The caret is just a button on your calculator. Multiplication is a button on your calculator. It's just a mathematical formula. However, the con of this method is that it leads to a lot of order of operations errors if you're not careful. Instead, we can look at option 2, 5e3. If we can get our calculator to show this, we will have the exact same value when we plug it in our calculator, and that will solve a lot of our problems. Your calculator will already interpret this as one number, so you won't see any of those order of operations issues. However, the downside is it's a little bit difficult to remember this E, and every calculator has it in a different spot. In order to get the E on a TI-84, you have to hit second and then the comma, which is above the 7. And it looks like EE, but when it actually prints out on your calculator, it's just an E. Moving on, we have our metric prefixes. You may have learned some form of acronym for this, or some sort of mnemonic. King Henry died by drinking chocolate milk is the one that I always used to use. However, this set of metric prefixes is not inclusive of everything we're going to use, and in fact it has a lot of prefixes that are very rarely used, so we're not even going to worry about that. Instead, we're going to start with our base unit in the middle. The base unit would be meters or grams or seconds. On either side, you're going to have 2 placeholders. As we go to the right, we're going to get smaller. So we have our base unit, 2 x's, and then a little m. This represents milli. 2 x's, and then we're going to use the Greek letter mu for micro. 2 x's, and the letter n for nano. Again, as we're going to the right, we get smaller. As we go to the left, we get bigger. Bigger than our base unit, our first stop is going to be kilo. So x kilo. Then we're going to skip, and we have mega. Skip, and we have giga. Make sure that mega and giga are capital letters. Each of these corresponds to a power of 10. Base unit is 10 to the power 0. On the left, when we get bigger, kilo represents 1,000, or 10 to the power 3. Mega represents million, which is 10 to the power 6. And giga represents billion, which is 10 to the power 9. Getting smaller, milli is the opposite of kilo. It's 10 to the power negative 3. Micro is 10 to the negative 6. And nano is 10 to the negative 9. There are more metric prefixes, but this is going to be representative of most of what we're going to be doing. If you can remember this, which can take some time, we have one method of converting metric units. So if I have 4.9 gigagrams, and I wanted to look at that in kilograms, one method would be to start with our 4.9. And we're starting here with giga. We need to get all the way down here to kilo. In order to do that, we need to move 1, 2, 3. I'm counting the x's as spaces. So we need to move 1, 2, 3 to mega, 1, 2, 3 to kilo. So we're going to start with our decimal, and we're going to move it 1, 2, 3 to mega, 1, 2, 3 to kilo. We're moving it to the right because I started up here on the left and moved to the right, filling in zeros as I go. That gives me 4,900,000 kilograms. Method 2 involves using our dimensional analysis, 4.9 gigagrams. Well, I know that 1 gigagram is equal to 1 times 10 to the 9th grams. That's what that 10 to the 9 means. And I know that 1 times 10 to the 3rd grams is equal to 1 kilogram. If I throw all of these into a calculation, gigagrams cancels with gigagrams, grams cancels with grams, and I'm left with kilograms, which will give me 4.9 times 10 to the 6th kilograms. Those two values are the same value. One is in standard notation and one is in scientific notation. It doesn't matter the method you use, you'll get the same answer. That's it for part 1.